Up to this point, we've been focusing on categorical variables. We want to shift our focus now to quantitative variables. So, a lot of the same techniques that we use to do hypothesis testing and to find confidence intervals apply. We're going to use a version of the central limit theorem here also. Um, Applied to quantitative variables, there are some different things that we need to consider. But just as a reminder, recall that variables are either categorical or quantitative. We've been focusing on categorical up to now. Now we're going to look at quantitative variables. Remember, if it's quantitative, if you can do mathematical arithmetic operations and it makes sense. The center expected value for a quantitative variable is the mean. If it's related to the population, we call that the parameter, and there's mu. If it's related to a sample, we calculate the statistic, and that's x bar. Going back, hopefully you remember the Gettysburg Address, that example we worked on earlier a couple weeks ago. It has a population of 268 words with an average length of 4.29 and a standard deviation of 2.12. Here is the population. There are all 268 words, excuse me, represented here. This is the number of letters in each word. And it also lists here, by the way, the center, in other words, that mean and the standard deviation. You may remember that we took a random sample of 5 words from the Gettysburg Address and figured out the average length of that sample of 5 words. Now, what I did here is this is using the applet, and this is the sampling distribution of the sample length of 5, found the average length of 5 words, and I took 140 different samples of 5 words. So there are 140 samples total in here, and these are the average lengths. This last one in blue is the average length for that last sample that was drawn. You notice the mean is 4.297, standard deviation is 0.912, and the number of samples drawn is 140. And you also see here, instead of saying letters, this is saying sample means, because remember, each one of these, and you can't see them individually. If it was a dot plot, you'd be able to, but there are 140 dots in here, or all 140 samples are represented in this histogram. Why are all the sample means not all the same? Well, remember, statistics vary. When we pull a sample of 5 words, would we expect it to be the same from sample to sample? And the answer is no. So statistics vary. We're taking different sets of 5 words. At what number do the sample's means tend to center? Well, that's right here. That's at 4.297. It's pretty close to that population average of 4.29. What's the standard deviation of the sample means? Remember, we're looking at here at what I had come up with when I ran the applet. Do you think if I ran the applet again and said, I want my sample size to be 5 and I'm going to draw 140 samples total, that I would get exactly a mean of 4.297 and a standard deviation of 0.912? And hopefully you think, no, I would not necessarily. I'll probably be close, but it wouldn't be exact because samples vary. Now, describe the shape of this distribution. And this is kind of a trick question in the sense of it doesn't really have a pretty shape. When I ask this in class, some people will say it's skewed, some people will say it's kind of symmetric, but remember, we have a very small sample size. The sample size is only 5 words. What if I did a larger sample and instead sampled 20 words? Now, we're going to look at the average sample length of 20 words, and we're going to once again pull 140 sets. Same question, why are the sample means not all the same? And as we said before, samples vary. At what number do the sample means tend to center? And it's pretty close to where it was before, 4.313. Now the standard deviation is the big thing that's changed. It's cut in about half. So as our sample size goes up, remember, it's going to help us with that variability. All right, so there's less variability. In fact, if you look here, compare the width here, that range to the range here, It's very different. Describe the shape. Well, to me now, this looks pretty symmetric. It doesn't look bad at all. It looks, yeah, we have this high peak here, but it wouldn't be a bad estimation to draw a normal curve approximately like that. This should feel familiar. The central limit theorem. There is a predictable pattern for sample means, as there were for sample proportions. If we repeatedly take random samples, each of size n, from a large population, and we'll talk about large in a moment, that has population mean mu and population standard deviation sigma, then the distribution of the sample means is going to be mu, and the standard deviation is going to be sigma divided by the square root of n. And that's helping us to manage the fact that we're not looking at the entire population there. So this is, though, assuming that we know that population standard deviation. We won't always, and we'll deal with that later. But for right now, if you know the population standard deviation, it's pretty easy to figure out the center and the variability. This quantity, the standard deviation of the sample mean, is often called the standard error of the sample mean. So you'll see it either as the sample standard deviation of the sample mean. It is called just sometimes the standard deviation of the sample mean, or the standard error. Either one is fine. We can say that the shape is approximately normal if either of these two conditions apply. If the population from which the sample is drawn is normally distributed, which we would pretty much have to be told, or if the sample size is large enough. Large enough, well, what do you mean? The more skewed the population distribution, the larger the sample size will need to be. As a general rule, we're going to use n has to be at least 40. So if n is more than 40, I should say, not at least 40, is more than 40, we can assume that we can use that central limit theorem. If it's very skewed, which I would have to tell you or show you that it's very skewed distribution, we would have to use n greater than 100. The validity conditions in this case are very simple. We have that 10% condition again, where the population is at least 10 to 20 times the size of the sample. If it is, we're good to go. Now, the sample size condition, if the population distribution is not normal, then there is a sample size requirement, and we're going to focus on n greater than 40 here. If the population distribution is normal, there's no required sample size, which is kind of nice. How will we know, though, if that population distribution is normal? Well, you can be told that, or you can check the graph of the sample data if you have it. If it looks fairly symmetric and bell shape, then we're pretty good to go. But we're going to focus in this class on n being greater than 40.